Hi students, this video is on reaction rates, and we're going to cover basically how reactions can increase or decrease in speed and which factors control those. So we'll look at really what a reaction is first. So reactions are just chemical changes in which products are formed. Well, reactants form one or more products. So products are formed here from these different types of reactions. These are just theoretical reactions. A plus B makes an AB. These are, it could represent real equations and do. Or like this one, a decomposition reaction where something gets separated. Or this is that single replacement type of reaction where these two things combine together and you end up with the same stuff but just rearranged. And then over here, this double replacement reaction where both partners change. One example of one of these types of reactions in real life would be like a combustion reaction where you've got carbon or methane really added to oxygen. And when those things react together, you get CO2 and water. Now, we've talked about this reaction before. However, this doesn't just happen to every single molecule that you put into, if this was happening in a car engine or something, for example, it's different fuel, but it still burns. So in this type of reaction, not everything actually will react because reactions aren't perfect necessarily, and not everything is efficiently reacted. And the reason is because, well, two rules. In order for a reaction to occur, two things have to happen. There has to be sufficient energy in that reaction. And what that means is that when the things are going to react, the molecules are going to react, they have to actually hit each other. And this is actually how the reaction takes place. They don't just find each other and magnetically, get together or something. It's random, really, how they're bouncing around and eventually run into one another. So in this case, different reaction, but I think this is ammonia and something like carbon monoxide. When those two things run into each other, they have to hit each other with enough force. If they don't hit each other with enough force, they'll just bounce right off of each other and go their separate ways. If they hit each other, though, with enough force, they will actually do the reaction, and those atoms will switch places, and that'll happen. Another thing that has to also be true is that the chemicals have to be oriented the correct way. And that means that they have to be facing the right way when they hit, or else the reaction still won't happen even if they hit with enough speed. So in this case, you have carbon monoxide and oxygen hitting each other in the wrong way, oxygen to oxygen, and there's no reaction. Now, if it goes carbon to oxygen, then you will get carbon dioxide formed and this single oxygen on its own. Doesn't matter that we study this equation per se, but just to see that it does depend which direction this molecule is facing in order for it to correctly react. So let's look at some examples here. So this is a reaction. Let's see. If I hit go, there we go. This is a simulation here where you've got the molecules here, A and B and C, running into each other. And if they have enough speed, like I just increased the temperature there, then they start reacting. But previously they didn't because they weren't hitting each other with enough speed. Now, if I not only hit them together with enough speed, but if I make that angle off, right, as you can see here, the angle is not dead on, then the reaction actually won't happen. So now they'll just start bouncing around, and then I've sort of shown you some other examples where they do hit each other, even with some tremendous speed. But if they're not hitting each other the right way, you're not going to get any kind of reaction happening. And you might ask, well, like, how can I actually make this a proper, or you can see here, they didn't hit each other the right way. It has to be the front of the yellow and the front of the purple have to hit, just like it's going to show here, in order to react. Okay, so how can I ever get a reaction to happen unless it's going dead on? Well, it's really hard if you just have one of each. But If I have lots of those things going on, let's see, I'm going to put a bunch of the A into this box here. Now, if I do that, I am able to increase the odds that the proper orientation and the proper speed will actually coincide, and that there will be reactions happening. You can see here, these bar graphs are showing I haven't really increased the temperature enough for most of these reactions to actually form products. So if I heat it up like I'm doing right now, enough of them will start to eventually have the right amount of energy, and they will combine to form products. So what are the ways that I can increase, or I guess manipulate those two different things, the orientation and the speed, or the energy they have when they hit? Well, there's 6 ways listed here. Usually people mention 5. I'm going to give a 6th, and that would be mixing, but we'll kind of go through each of these one at a time. First would be temperature. Just heat it up. And when you do that, you increase the speed of the particles. That's what I was doing in the little simulation there. The second would be concentration. And that's in the solution to just increase how much stuff is in there. The more stuff that's in there, the more reactants are in there, the higher the chances of successful collisions are. Okay, so increase the concentration. Increasing the surface area. So if I, or modifying the surface area, if I have a solid and I want that solid to react, if I break it into smaller pieces, it's kind of like increasing the concentration, right? I'm allowing more surfaces for that solid to react with the solution, for example, or the solvent, for example. So it will dissolve and then start to react while it's in solution. If you're working with a gas, then those gases are the best candidate for a chemical reaction because they're already all bouncing around like you saw in the activity, and liquids are kind of a second best situation because liquids still move around pretty randomly, but there's a little more constriction with liquids because the particles can't move around as freely as a gas can. And then the fourth one is a catalyst, and I'll expand on this in a minute. A catalyst essentially holds molecules in their proper orientation and lowers their activation energy. Okay. That term activation energy, by the way, basically just means how difficult it is for the reaction to happen. You might have seen it in the last slide where this thing right here is showing how difficult it is for the equation to happen. And then as you go up this curve of energy, this is what we call the activation energy right there, this little part of the curve. And in order to get this reaction to happen, I have to overcome the energy of activation in order to create reactions, to create products, excuse me. And then lastly, pressure. The increasing pressure on a gas is kind of like increasing concentration, but again, it has to do with gases only because you can't increase the pressure on a solid or on a liquid. So it really just has to do with gases. And I'm going to give a 6th kind of extra one, and that's just simply mixing. And what mixing does, of course, is help dissolve things faster or just move things around. And you're kind of like increasing the interaction of all these things. That's why mixing helps that reaction rate just increase naturally by increasing the number of times things can hit each other. Okay, one final comment, and that would be on a catalyst. So a catalyst is this is a catalytic converter. I'll just sort of write that in there. Now these are on cars, and they get stolen all the time because they have really, really rare metals in them. Things like platinum. Platinum. I think that's how you spell that. Or palladium. So those are really rare and expensive metals, like things people make jewelry out of even. And the reason that they're in there is that they help these reactions to take place in the exhaust. So before the exhaust exits the car, it goes through the catalytic converter, and it's a chemical substance, in this case platinum or palladium, that increases the rate of the reaction, but not it's not an actual reactant in the chemical equation. If you look in these equations, palladium and platinum are not in it. What they do is they hold those molecules in the right spot in order to increase the rate of reaction. I have an example for you. So here's a short animation that shows how a catalyst works to increase the rate of reaction. What it does is, this is the purple object, okay? This is the catalyst right here. And the catalyst holds these things in their proper orientation. So when the green and orange object comes in, that's a molecule here, and then the blue object comes in, they get held in the kind of the arms of the catalyst, and the catalyst helps them find the right orientation in order to make the chemical reaction happen. It also provides a little bit of mechanical stress, helps the bonds break a bit easier, so it does that as well. In our bodies, in biology, these are called enzymes, but there's also other types of inorganic catalysts like platinum, palladium, iron, even lots of other types of metals are catalysts, and they increase the rate of reaction, and they're really cool because they never get consumed in the reaction. You can just keep using them over and over and over, and they just increase the reaction rate by being there. So I hope you learned that there are different things that modify the rate of a reaction. There's sort of 6 listed here, and they help basically do 2 things: either increase the speed, the energy really of which things hit each other, or they help things get in the right orientation, or are more likely to find the right orientation just by sheer chance. So I hope that was helpful.